Everybody, can you hear me? Yeah. Okay, welcome back, everybody. I would like to introduce our keynote speaker today. Valerie Taylor is the director of the Mathematics and Computer Science Division at Argonne National Lab, and I'm proud to call her my boss. Uh, Valerie's earlier career spans a stint as a faculty member at Northwestern, from which she moved to being a faculty member at Texas A&M. So, like Chameleon, her career spans Chicago and Texas. So it's a great connection to the project. And then Valerie is known for her research on performance analysis, HPC, and more recently, power evaluation. And the most power efficiency. And most important thing is she's a Chameleon user. So she will tell you about fabulous research in the area of AI on Chameleon. Take it away, Valerie.
Thank you, Kate. And I think more as a colleague than. Okay, so is my microphone on? Are we good? Okay, so I just want to say I really enjoyed the panel on education. So that was so engaging. And I'm going to do a bit of a switch to talk about some research that we've been doing with Chameleon. And because we're doing work with energy efficiency, that's where Chameleon was really beneficial. And I think this came up during one of the presentations where you were looking at power and you had power on CPUs, but when you get to power on GPUs, you need to have the drivers for those specific GPUs. And when you go on a production system and say, I need to install these drivers, you either put in a ticket in which you wait, or if you go, I can do the installation, then they look at you and know you're joking. Like, you've got to be joking, please. So this was great. So I just want to tell you about our research, but I'll talk a little bit too about what we did with Chameleon. So first, in terms of this work, I want to acknowledge the team. That includes researchers at Argonne and also UIC, and that's University of Illinois at Chicago. So it's a great group. So with Chameleon, it provided the bare metal platform for the experiments. We were able to get the time we needed, which was great. We were able to get the dedicated access that we need to actually do the measurements and have some confidence in the measurements. And we did a large number of measurements. So just to go a little bit more into detail now, to frame the work that we're doing, and that is looking at large language models for software generation, but then I'll go into detail about the energy efficiency. But if we put this in context, I think everybody's been hearing about the use of AI for a computational assistant. And that is when you look at that use of AI for a computational assistant, you'll start off with an open problem. You may do a mathematical formulation, do some maybe numerical formulation, and then from there you want to go to an efficient algorithm, have the parallel implementation, do some type of simulation, have the analysis, and have the feedback. You may also have some experimental work that comes in, but you have this aspect of looking at how AI can be used in terms of this whole cycle, in terms of what you're doing for computing and understanding computational science. So when we look at this, the part that we focus on has to do with efficient algorithms and also the parallel implementation. So when we look at also the reason, and I think everybody recognizes this, the reason that LLMs work so well with code generation, and that is you have different syntactic and semantic rules. So it's very much rules-based when you look at programming languages. Also, there's an abundance of open source repositories that's available for different code segments, some more than others, such as Python. You can find an abundance of code repositories. but maybe not so much for Julia. Then you can also, oftentimes, when you're looking at code, you have well-defined tasks that you want done, which lends itself very well. Then you can have code that's modular. So you can have it work on different pieces of the code and then build up to something more complex. And it's important for the scientific process. So when we look at the full scope around large language models with code generation, there's many different aspects. There's correctness and reliability. There's also around prompt engineering, because a lot depends on how you prompt. Then there's also security and safety, performance and efficiency. There's maintainability and readability, license and attribution. I want to note when I talk about correctness and reliability, there's also the aspect of reproducibility that comes in. The part that I'm going to focus on is a little bit on correctness. There's a lot more that's needed in that space, but also a lot more that I'll focus on performance and efficiency. But I just want to note the full scope of things to look at with scientific code development. So for my talk, I'll talk a little bit about our early work that had to do with using large language models for code translation. So that's when we started about 2 years ago. And so that was very interesting. Then we extended to energy efficiency, and that's been where Chameleon really played an important aspect for the energy efficiency, and then talk a little bit about future work. So with Lassie, when we started off with the project, we were having fun using LLMs. And so we were joking around, it's like teaching an old dog new tricks, okay? And so someone asked me, who are the old dogs? And I go, we are, okay? And I included that person in that group, we are. So hence our name Lassie, which is LLM-based automated self-correcting pipeline for generating parallel scientific codes. So how many people are aware of the show Lassie? Okay. So see, our Lassie has glasses, okay. That adds the intelligence. Because Lassie was this, Lassie was this dog that anytime you were in trouble, it didn't matter if you were 10 miles away, 20 miles away, somebody would go, Lassie! And Lassie would run and suddenly appear to help you out of a well or whatever. So that's the show. Okay. So we try to have a little bit of fun with it. So here, in talking about using it for translating code, that's where I'm going to talk about. We actually ended up with a pipeline, and that's what we're talking about, this self-correcting pipeline, where we did a lot of self-prompting. We get feedback, because you can have compiler errors, you can have execution errors, and so we want to have that feedback. So I'm just going to show, we did some work of evaluating translation between OpenMP and CUDA. And we did bidirectional, but I'll just show a little bit of the results. And we did 10 code segments, and at that time we used some early, about 4 large language models. But now, and I'll show what happened when we used some large language models that are more current. So we'll talk about that in a moment. But in terms of the prompting strategy, what we did, so we start off, and it's independent of any large language model. So you can plug in any given model that you want. And so we'll start off with a prompt, as you usually do, like you're a professional coding assistant that specializes in translation, and we give that. And so what we start off doing is first, with respect to the source code and the context, so that's where, because we're doing the translation with CUDA and OpenMP, We used some material from the reference guides, depending on the translation. We also, at that time, imagine 2 years ago, I know a lot has changed, but we took the minimum of the context window size, which was about 16K tokens, and we also had the original code. So we had the source code and that curated content, and we would feed that to the LLM to generate a summary for us. Then we also provided a description of the code that we were using, and that provided our context. So that way we had LLM that was familiar with the code, having gone through the code base to say what's the functionality. So then here we're using all of that information to generate our prompt, which then goes through, generates the code. We may compile the code. If it fails, we do a correction prompt back to say, here's the error, so you should be able to fix it. And we had a number, like if it didn't fix it after 10 tries, it would stop. But we actually had self-correcting, which usually about 1 or 2 attempts, so it wasn't where we ever had to get to that point. We also did execution. And here, because we were working with a benchmark suite, we looked primarily at the output of the benchmark to actually see, because we were just doing code translation. But when we get to the energy efficiency, I'll talk a little bit more about what's needed there. So we would generate again, and then let's say now it executes, so we can save the code and also the metadata. And by metadata, we're looking at how many correction loops we actually had and things like that. So just to go over this real quick, so here's our benchmark suite where we use HeckBench that came out from, this is with Jeff Vedder's group at Oak Ridge, and he published a paper about the benchmark suite, I think in 2023. It has about 350 different benchmarks from various sources. The good thing about this benchmark suite is that it has the benchmarks in many different languages. So it'll have C++, OpenMP, CUDA. So you have all these different versions of the code that you can do the comparison with. So because we were doing translation, this was a nice benchmark suite to work with. And then we just used here NVIDIA A100, we were just collecting execution time. So that was pretty straightforward. So here's the different LLMs that we used. So you probably will laugh, oh, that was back, 2 years ago, Cold Stroll and Wizard Coder. And that's when we were using GPT-4. So. But just want to give some results because we extend this, but here, that is when we looked at the codes, and when we looked at this, we had 80% of the codes we were able to translate from OpenMP to CUDA, 85% from CUDA to OpenMP. When we looked at runtime, 78% of the codes performed well. That was within 10% or even better than what we had in the benchmark suite. And 62% performed within 10% or better from going to CUDA to OpenMP. So this table, which you probably can't read very well, but it's just to say you're starting to see some NAs, and the NAs are where we were unable to get the translation. But now, when you have reasoning models, so reasoning models, you just see a really big difference with reasoning models. So the reasoning models where we started with GPT-01 preview, here, the interesting thing is that we were able to do the translation for all 100%, and it was only in one case that it had to go and do one self-correcting loop, okay? So reasoning models now, where you're taking some time to reason, and it was the chain of thought, reasoning, and you're giving that context, it does much better in terms of the code translation. And we also wanted to explore what happened when we actually had context versus no context. So we were trying to explore different avenues. And this just gives you some of that data, but the context was 45% better improvement in terms of being able to have the translation. But you can see with the O1 preview, which is the reasoning, the one reasoning model, we were able to get 100%, but both ways with the translation. And so now reasoning models are common in most LLMs, and so you're seeing you can get really high rates in terms of the code translations. However, so now the next question that came up, okay, we gave us a chance to play around with the code translation. And this is where we wanted to extend to energy efficient. And that is recognizing that energy, if you look at it, is the capacity to do work. So energy, you look at it on average, you can look at it in terms of your average power times the execution time of your application. And so this gives you an opportunity to look at trade-offs between execution time and also power. But it's influenced by the hardware, the software, also the workload and system, but especially the hardware, which means, like for example, in current hardware, where you can have low precision 4-bit, 8-bit operations, that results in significant energy savings versus doing 32-bit or even 16-bit operations. And so what we wanted to do, and also in different architectures, you'll have a different memory subsystem. So how do you take advantage of that memory subsystem? So it's not where you can just say what I have for an A100 will be the same as an MI 100 or an AMD versus a GPU. So you need to take into account some aspects about those systems. And so that's where looking at energy efficiency, when you look at large-scale systems, and you hear about this now quite a bit with data centers, you look at environmental stability, sustainability, not stability, but sustainability. Also with large-scale systems, such as exascale systems, it's the cost in terms of providing that power. Oftentimes, you have to do restructuring of a current facility to accommodate the power requirements. So that's important. Then you're looking at also, it becomes also an innovation driver to look at the energy efficiency, because now you can, within a given budget, you can do more work as well. So here, now it's a little more complicated in terms of the pipeline, and I'll go over this. But so what we're doing now is that our context, in addition to looking at the code, we're also looking at the target hardware. But it's not just taking the target hardware without doing some execution on that target hardware. Because you want to know if the refactoring of the code actually resulted in better energy efficiency. And so we thought estimates, while they're okay, it doesn't give you the best insight because there's a lot more that goes on in a system than what we parameterize in terms of models. And so here, that's where we're doing some measurements. So when we look at LASI EE, we'll start off with stage 0, where we're doing some code profiling. So we'll do the power profile of the code that we're starting with as our stage 0. Then we'll go through and just note here where we want as our baseline, we're just giving an LLM and say, make it more power efficient or energy efficient for this target architecture. We're giving it context, but we're just doing a zero shot and have the efficiency that results from what we call baseline code refactoring, okay? And that's very similar to the LASSI original framework, except here we're looking at energy efficiency, and because we can have significant changes to the code, we actually have an agent that's doing a lot more than just checking the output. The agent is also checking the functionality, that you have the same functionality of the original code that you have with this code. So it's doing a lot more checking in terms of that new code because it's changed a lot more, okay? Here, stage 2, so now we have stage 1, it gives us that baseline. Stage 2, this is where we actually do a lot in terms of looking at the context for the target platform and also doing a planning. So here, with the context, what we'll do is to prompt the LLM to say, give us a refactoring plan, okay, for this target architecture where you do have some initial power profiles, because you have the power profile from the code, profiling from stage 0, and also from stage 1. And you can use that to help you to get information about the target architecture such that you get a refactoring plan. Okay. Next, stage 3. So this is where we're going to iterate through the refactoring plan, because it doesn't do all the refactoring at one time. A lot of times you'll have a prioritized refactoring. And so we're going through, and we'll go through our refactoring plan and do piece by piece. But what we're doing here is we're iterating through the process to identify if we did, when we refactor the code, did it give us a better energy profile? So we're doing measurements at this point as well. So we're constantly doing measurements. So we need an infrastructure where we can reserve, schedule, and upload our drivers and do these measurements. Okay. So Chameleon is right there. Okay. And then we can terminate. Let me just add with stage 3, what we often do here is to look at some number of iterations. So just to go through this, let me just mention this back. We go through 10 iterations, okay? So if we have 5 iterations where it doesn't have a good improvement in energy efficiency, we stop. Because you kind of go, okay, after 5 iterations, let's not keep going. However, you may go 2 iterations and then restart. And then you have the third one, you end up with better energy efficiency. So another condition for stopping is to say maximum of 10 iterations, okay? Because we don't want it to keep going. So here's an example of where we're taking a Jacobi. And so here, and this is using Chameleon, where we're using the NVIDIA A100. It's an 80 gigabyte. So we're starting off with the code profile, and it's about 7.9 seconds, and we have about 1.2 kilojoules in terms of the energy. And we do take measurements so that we're taking off idle power. So now, the next stage, where we're doing stage 1, where we go through here, and this is where we used a reasoning model, we use GPT-03 Mini. So in this case, what we did was we said, now generate more energy efficient code, and we wanted to make certain the LLM as a judge agent. That becomes important because it's changing the code. So now we ended up with about a 30% energy reduction. Okay, kind of go, oh, that's pretty good. So next, we generate, this is where we start to generate a refactoring schedule. And so here, that's where first to generate these refactoring schedule is first going through, and it uses the programming guide, hardware configuration, and a source code, but it first goes through and identifies code inefficiencies within the code, and then it'll give you a refactoring plan. Okay. So now when we go through that stage 3, where we're doing this iterative self-prompting, because now we have this refactoring plan. So here we can see a better reduction within the code. And so this is where we're going through, and what we can see in terms of some of the refactoring that was done was it did pinning to host memory, it did cache preference of working with your memory hierarchy. It did also a dedicated CUDA stream for asynchronous error copy. It also did a lot of more asynchronous memory operations. So it's going through and looking at where you have code inefficiencies and generating a refactoring plan and actually refactoring the code. So here, and this is what we found in terms of, just to give an overall example of where we're taking the LASSI EE and going through that stage 3. So here, in terms of the LLM comparison, because what we do once we have the code that works the best in terms of best energy efficiency, we also ask the LLM to give us a difference, summarize the difference in the code, because it's gone through and it may have done several refactorings. And so here, this is where we find where it did fuse iterations in a single kernel, eliminated swapping, improved memory transfers, and it did a lot of asynchronous operations, so reducing the synchronization, and it reduced the error computation overhead. Because in Jacobi, you're iterating to get to solve AX equals B, and you're iterating until you get to a solution, because you're not doing a direct solution, it's an iterative solution, until you get to within a given error. So that's what that error is corresponding to. So this gives you some idea of the refactored code, but it ended up with about a 46% reduction in energy. So we were really happy.
I'm sorry, maybe you've mentioned this
Oh, no.
before, but how do you make sure that what you refactor is actually correct? Because these models, of course, can remove code and then becomes energy efficient.
I know, it can just do a print error.
Or something a little bit more subtle. It looks like the same code, but it's dropping some corner case or something.
Right, so that's where we do a lot more in terms of LLM. We have an agent that's going in to look at and say, what's the functionality of the code, in addition to looking at a number of test cases to actually look if you're getting similar output. And that's, we recognize that it's not going to be exactly the same. There could be, we have error bars that we allow. Yes.
So since you are not trying to achieve bitwise identical, and then you say like there are some error bars, so how do you determine the error bars?
So here we actually looked at, we said we just wanted like 1% error. We actually set it. Yes. Oh, are we okay?
Yeah.
We also do see some configuration changes. So the type of thing where you call refactoring could involve also configuration changes across the stack, because
Can involve, what was it?
configuration changes, like
Across the stack?
yeah, like at line 2, I do see that you set the cache config for
Right.
CUDA.
Right, so we can do configurations that can be specified in the code, yes. If it's configurations outside of the code, we don't. Yes. So if there's a system, a configuration that requires that it be done before you start your code that's not programmable, then we
Everything
don't.
that you can program it, right?
Right.
Thank you.
So here, and I'm just going to give some initial results. So here, and this is where we use, with the Chameleon, going into a little more detail, we use the testbed nodes at UC and TAC with AMD EPYC, and then we evaluated the applications on 2 different GPU platforms. So we used the NVIDIA A100 and the AMD MI100. And here is where being able to install the NVIDIA driver version, 56.35.05, it gives us the ability to actually go in and do the power measurements. And the same with the AMD MI100. Again, that gave us the ability to do power measurements. So we don't have that on other systems. We've asked, but we thank you, Chameleon. So I just have to say, this enabled this research. So when we did the energy efficiency, we went to 22 benchmarks. We wanted to have a larger suite. The first one of the code translation, it gave us an entry into working with LLMs and working with code, but now we want it to be a lot more detailed. And so we use some also mini apps as well. So here's some of the results. Don't worry about trying to read it. Okay. But I'm just going to tell you what we have in there. So we give results from both GPUs. Here's the energy savings. We can get also the power savings, runtime. This gives you the best trial, so it tells you if it had to do self-correcting, in which case, in many cases, it did not. But it tells you also which iteration we actually used in terms of the power. Sometimes we had to go into the last iteration. And then the average pipeline time. So this is not all of them. This is only about half of them, but just to give you a sample of what we have. And just to go a little bit more, so here, this is a good case where we had significant reduction in both power and time. Here's a case where it was after the first trial. This is where we actually found the best energy efficient code refactoring. So, and here's a case where the best candidate for the MI100 was found much earlier than the A100. So it gives us an idea that we're using different refactoring schedules that are based upon the target architecture. And just to give a little bit more too about different optimization strategies. So we classified our optimization strategies into 4 areas, one being memory hierarchy optimization, another one being algorithmic and computational efficiency. So this is where we can look at loop unrolling. We can also look at branch hoisting and things like that, of taking a branch outside of a loop. So we also did parallelism and thread management, where it may have combined threads or group threads, especially in terms of memory sharing. And then some device-specific tuning. And that may be if we can use lower precision, depending upon what we're doing, but what were specific aspects about that architecture. And it was interesting to see, so you can see it was a nice distribution. It wasn't where one area for optimization dominated. So you needed a combination of areas. And then it was very interesting to see with the two different GPUs, that they had similar distributions among the different benchmarks. And so that is the top for both was actually the memory hierarchy optimization. And the one that was used the least per se, and that was parallelism and thread management. So it's very interesting to see that. So just in terms of the results, and that is, and let me just provide a little more clarification here. So with our runs, where we would take a benchmark and go through that pipeline, and we may iterate up to, including the first iteration, maybe 11 total. We ran that, each one reran 30 times, okay? So each of those pipelines for each benchmark, okay? And the reason for doing that is we recognize, for example, the refactoring schedule that you get from large language models is not deterministic. You have some randomness in there, especially dependent upon the temperature that you set with the large language model. And so that was the reason for running it 30 times, okay? Because we wanted to get really good data. And what we found on average, that the energy savings was about 36% for AMD, about 34% for NVIDIA. And it was very similar in terms of the biggest reduction was in the runtime, but you also had reduction in the power. And then I just want to go over one last thing, and I only have 2 slides on this, just so you know. So you don't think I have another 15. Okay, so this is just 2 slides. So I'll finish it in 45 minutes. Total time for the talk. But here, what we looked at was, given we had all these experiments, we wanted to know, because you have some randomness, what's the likeliness of finding the best energy efficiency after, let's say, K is equal to 1. So that's 1 code candidates where you're going through the pipeline. After maybe you have to do 3. Was 30 too many? You know, so what we did was to look at using a Monte Carlo sampling to actually give us expected values for, let's say, a code candidate passing, in terms of that, where K is our number of runs. So if we're doing 1 up to 30, and then we're looking at C as the codes that pass, in terms of passing, where it can go through compilation and execution. And so that's where we have a pass at K, just to tell us, because we do have some randomness in the schedule that's generated, you know, do we need 30 runs? Can we get by with fewer runs? So we did a pass at K measurement or metric. We also, and that's where you're looking at, for example, N choose K, or looking at combinatorics. And here we're doing an energy reduction at K, and that's telling us, are we able to get an energy reduction? And what we really want, and that energy reduction, the middle line is just valid, meaning that it resulted in a lower energy than what we started. And what we look at in terms of that parameter is an energy reduction at K that combines both the pass at K and a valid energy reduction. So how many experiments do we need to do? We did 30, but we wanted to do some sampling to get an expected value of what happens if we do 1, 3, 5 experiments just to see. And what we found is that, for example, the pass rate, when we have K is equal to 1, where we're doing that one lassie, where you're going through 10 iterations, we see the pass rate is around 81%. When we go K equals 3, it goes up to 97%. And if we go K is equal to 5, it's 99. So we could probably get by with K equals 3. Okay. Then when we looked at, and this goes back both devices, AMD and NVIDIA. So when we look at the expected energy reduction, how much better do we get with different number of code candidates that are generated? When we have K equals 1, it's around 29%. When we go to K is equal to 3, that was the interesting part, it was 48%. Then when we get to K is equal to 5, we're around 54 or 54.6%. So it tells us that we don't have to do the 30. We did the 30 so we could do the experiment to see, but we could probably do maybe 3 experiments to get to some good results, because you do have that randomness in terms of the refactoring schedule that's generated. Okay. So wrapping up, so in terms of some of the insights, it's important to have the context with the large language model, to have it also be iterative, and to be self-prompting with the refactoring. Also, you need, well, we actually found there's a large number of optimization strategies that depends upon the code and the target architecture. So we didn't limit any optimization strategies, which we found was really good. We recognized too that while we looked at functionality and we did a number of tests with respect to the agent that was the judge to say, is this refactored code same functionality as the original code, we recognize that more work is needed because when we had some outliers, it was a human in the loop. Okay? So we did check on these things. Then here, it's really good that large language models can be used, especially reasoning models, when you're using cross-language, cross-architecture extensions. And then here, it was really good, the data. So we've archived the data that can be used also in terms of post-tuning of models. So having that data and the metadata available, we're looking at it in terms of doing some post-tuning of models. So it was really interesting. Then just want to mention there are a number of different methods that are looking at energy efficiency. Some of them are, quite a few are static, or looking at it, and that's with like copper. Some of them use like a performance model to actually help guide and say a performance estimate, and we just didn't feel comfortable doing estimates. But it's a lot of work that's too, where people are starting to look at the performance of the codes a lot more, which is good to see. So it's not just having the code that's generated, but you want to have performant code. So with that, I just want to wrap up at the end by saying thanks to Chameleon for enabling this work, because that bare metal platform where we could download the drivers that were needed to do the measurements enabled this work. Without it, we would still be asking if we could get access. We were able to get the time we needed, and that is to do all the experiments that were needed. And then it also provided dedicated access, as you can see. So I'm wrapping up with what I started, but now having seen it, that we really did need to have some dedicated access so we know about our energy measurements. And ending with where I started, with acknowledgments. So that, I'll say thank you.
Thank you very much for a fabulous talk. Any questions for the speaker?
Okay.
You go first.
One of the things that there's been somewhat arguments about is how much does optimizing for energy efficiency differ from just optimizing for performance? And I'm mostly in the camp of if you optimize for performance, you've optimized for energy. So how do you think this work would differ if you were planning to optimize for performance rather than energy?
Would differ, and I can go back and show you. In the table, there's, I think, one entropy where it was a reduction in power, but not a reduction in execution time. Okay, and that's because of the use of a particular resource that you have. So your resources, the issue that comes up with power is that you have different distributions of power usage by different resources within a GPU and a core and CPU. So depending upon how you use them, that can determine your power. It can also determine your execution time, but it's not always the case that it's execution time, because you can use a different resource that's less power, but you didn't pin it to that memory subsystem. And that's what we found, that when we did the pinning, it actually resulted in a lot less power, but it was the same execution time.
Okay, as long as it's the same execution time, you win for sure. That's why I was curious, because if the execution time ends up going up, the idle time on the machine will dominate any optimization for energy. That's why I was curious, yeah.
Right. Mm-hmm. And then sometimes and what we're seeing is you can do both.
Yeah.
And that's the part you want to do. So, but to do both, you need to understand the power distribution among your resources and how to best use them. Yes.
Do you have estimation of the token cost for example, the factoring 1,000 lines of code?
The total cost?
I mean, the token cost.
Oh, the token cost. Oh, we tried not to. It's and I'm just trying to think, was it 1 million tokens? I have to get you the exact number, because we took out token cost from this, because we were using, for example, the large language models that are available at Argonne, and so we weren't paying for them. Argonne was paying for them, and I know Argonne's budget went up. And we took out the token part and said, let's focus on the energy efficiency part, and so I can get you the exact numbers, because we do have it, but we just, yeah. I'll have to go back and see. Okay, because it's just 1,000 lines of code, so it would be those two applications. So I have to go back and see that. But I'll let you know by tomorrow.
Sure.
A couple of questions here.
Yeah, thanks for the talk. I know it wasn't your focus, but I'm wondering if you could offer any subjective thoughts on the quality of the code that's generated, so the readability, maintainability, extensibility.
Okay, and here's the part. Because we started with code that was readable from a benchmark suite, it's not we understood the code that resulted. And I'm just, we didn't necessarily have, what was it? Comments in the code. I guess we understood the code, but maybe it was because we had looked at the code, original code. So it's hard for me to say that, let's say if someone who had not looked at the benchmark codes, looked at the two codes and go, yeah, this is the same level of readability exists. So I think we're a little biased because we knew it was refactoring, so we were looking for the differences. But yeah.
Thank you.
But that's a good question. I'll go back and, and ask that question. And maybe, it makes me think about this. Maybe we'll take our refactored code with people who have never seen the benchmark code and just to ask that question and see what they say, but do a sample. Okay. Yeah.
I have a question actually about the power measurement itself.
Yeah.
So because you're using the NVIDIA and the AMD drivers, you're getting the power that those driver stacks measure. Is there a risk of this optimization just moving power usage from the thing you measure to something you're not measuring? I'm thinking particularly for like the multi-node case, if somehow something gets, say, more network heavy or starts offloading more work onto something that's not part of what you're capturing.
So here, in terms of and that's a good question. Our experiments, we focused on a single node. So we didn't have to worry about the network measurement. So that takes that part out of the loop. But here, and because we were focused on a single node, we felt pretty comfortable with the measurements by the vendor drivers than things that were external to the node. So that was the part. That's a good question.
I think my follow-up to this is, because I work on kind of providing this kind of information, is there some, end-to-end measurement that we could provide, or what would be helpful to help answer this question in the more general case?
Oh, okay. Let's talk a lot more, because yes, having the vendor specific was really good with a single node, and it gave you a lot of measurements across the different components. But when you go external, that is an issue, because now the vendor, it's often a different vendor for the network. And then, you need to have the measurement on the NIC and things like that, and that's not captured. The NIC is not captured. So, yes.
Yeah.
You want to capture that. That would be really good to, yes. Yes, and what is your name?
I'm Mike Sherman.
Mike Sherman, okay. All right. So Mike will be in contact. That would be really good.
There's one more question over there.
Yeah, so I'm convinced that LLMs have the ability to optimize code. I'm trying to understand, or I'm curious to know what's next. Where do you see this going? So I know that Meta has something similar called kernel evolve, where they evolve Triton kernels. But I also know that they are not currently using it for whatever reasons. So what roadblocks do you see in this being adopted, or do you think it's ready for production systems?
So I think a couple of things, and I think the question that you have is being able to, so this one we did, where we worked with a given benchmark suite. We also worked with, single nodes. And a question that comes up is, if you want to go where you're just going from a description of what you want to now energy efficient code, now I think there are some companies that are working on that, but some of the roadblocks, like there's this company I was just looking at, Blitzy. I don't know if you've heard of that. Okay, and it's looking at, what it does is you have to give it a very detailed spec for what you want. So it's not where provide a solver to do this. No, you have to give it a detailed spec, because then it's taking that and its agents are taking and going into modules. And then each agent works on a module and there's a lot of orchestration. So some of the things that I think are important will be, for example, being able to do end-to-end performance and power measurements. You also probably want to do like memory footprint. So you want to do detailed performance measurements, not just timing, but doing detailed performance measurements and having that information feed back. So you have self-improving models that's using that information to feed back and self-improve. But I think we'll get there in some time, but there are these roadblocks of the measurement, being able to conduct the measurement, and also specify correctness, reproducibility, maintainability. Yeah. So it's plenty of research to be done. So, yes.
Very interesting. One thing that I've noticed within like the HPC community is that sometimes there's a cultural resistance to worrying too much about energy efficiency. You have to think about node hours or core hours depending on the machine that you're operating on. So that's always a bit odd for me because I work a lot with edge devices where energy efficiency is very crucial. So I'm just kind of curious, have you thought about trying to port some of this work into for systems that are more edge computing based, where you have like a very strict energy constraint because maybe you're operating a device that has a fixed battery that's attached to it and it only has so much charge to go before it powers out?
So we have started discussions about it. And so, and that's where we were looking at Chameleon with the Edge platform. So we just started looking at it because it is a case where energy and power becomes really important because of your budgets that you have with the devices. But I think HPC is coming around about energy efficiency because you have, exascale machines that require, 40, 50 megawatts. You have data centers. The data centers are exceeding expectations. So you have a lot now where a lot of discussions on energy efficiency, but I think the edge computing would be something good to explore, and we would be happy to work with you. Okay.
Okay, thank you again.
Thank you.
Um, all right, so we're gonna head straight into our second panel. Thank you so much, Valerie Taylor. That was a wonderful presentation. I'm guessing you're gonna get a lot more questions after the at the next break. So we're gonna, as I said, we're gonna jump straight into our next panel quickly. Our moderator for this panel is going to be Bogdan Stoika from the University of Illinois, a longtime user of Chameleon and also has organized a lot of artifact evaluation initiatives on the platform. So I'm going to turn it over to you, Bogdan, and just quickly introduce the speakers, and then we'll kind of move to the presentation.
Yeah, sure. Hey, everyone. Nice to be here. Our first speaker today is Aaron from the University of Texas at El Paso. And the entire session will be about agents. So we will have 3 or 4 talks about agents. So Aaron, the floor is yours.
So I am Irene Rahman. I am a PhD student at the University of Texas at El Paso. And I am fond of working with research that has to do with risk assessment of critical infrastructure And I've also been interested in network anomaly detection in high-performance computing systems. So over the years, you might have noticed that the research that revolves around HPCs, they mostly focus on the efficiency of high-performance computing systems, as well as how we can speed up such systems, right? However, there has been very little focus on cybersecurity aspects revolving around this area. So that's more like the problem statement, that what motivates us. And also the existing network intrusion detection systems, they heavily rely on network telemetry alone, flow features. And therefore, we wanted to get an idea of what it would look like if we could integrate system-level features or hardware-level features along with those flow features. So here you can see that the test bed over here, that we have a bunch of clients and servers. So we have an adversarial node where we run our attacks. The attacks are being generated using Metasploit framework, as well as some of the attacks are scripts that we manually design. And then there's normal data reaching from some of the servers to the clients. And we also have an aggregator node that is collecting or like pulling all the matrix so that we can have this unified data set, which we later feed to learning models. So we focus on 8 attack categories, and our focus is on attacks that are specific to high-performance computing systems. So moving on to give you a little idea about how we carry out, because you'll see that we collect around 2,600 features, but we narrow it down to 369 features using gain ratio-based selection. And the strategy mainly involves like ranking the features. And in this case, when I say features, it's just the system level features on which we carry out feature selection. We rank them in the order of their gain ratio, and we take subsets of features like 10%, 20, 10, 12, 14, all the way up to 20. And then, so this is a slide just to reflect on what the gain ratio is. I'm not going to explain it. I'm just going to skip it. So what we do is we carry out, we take the data sets, the feature subsets, and we fit it to all 13 learning models, like you can see over here on the right-hand side. And you'll see that for 12%, the F1 score has a peak of 0.81. So we consider that to be the best subset among all the subsets that we have. And we further move on, we further carry out the classification task. When I say classification, I mean the models are classifying whether it's a normal data or an attack data, focusing on 4 different categories. One is where we use all the raw system level matrix that we collect, and then the best performing feature set that consists of just the system level matrix. And then another configuration is where we feed the models with raw pickup features, or in other words, like flow features. And the one at the very right-hand side is where we combine both of them. That is both the system level features and the network level features. So it clearly gets, it clearly performs better. We achieve an accuracy of 0.93 and a recall of 0.88. So we can say that the system level features do complement the network level features when it comes to detecting anomalies in such systems. So I will be talking a little bit about the infrastructure requirements and usage, and that's where Chameleon comes in, because I would like to thank Chameleon because we were able to use the bare metal. And our research really requires access to these low-level telemetries, and Chameleon's bare metal does allow us to get access to those low-level hardware counters, which we needed. And so our focus was on studying how like the cache behaves, as well as like the branch events and memory subsystem matrix and so forth. It might be a little difficult to carry the to get access to all these counters in other commercial platforms. And also another thing is that our stack needed to be reproducible, right? So what we did was we created Docker images. We had like 2 Docker images. One was like a base image that could be used in all producer nodes, and another was the adversarial nodes Docker image. So that was specific to server 2, and we just took the Docker images, we pulled it, we deployed it to Chameleon, and we could start working right away. Okay, moving on to the challenges. So, well, this slide might not portray all the challenges, since the slide really focuses on the challenges associated with the workflow. But I figured today that it should have focused more on the challenges that I faced while using Chameleon, right? So I would say that the object storage in Chameleon, of course, it does help us to like archive the data, but it could be a bit faster in terms of, because like we have these large PCAP files, and when we're trying to transport them and like store them, it does take quite a bit of time. So it could, could make our work a little more efficient and smooth if it was a bit faster. And also, I was actually advised by Mr. Hammock, yes, that the data analysis could actually be carried out in a separate in a separate node apart from the bare metal, because bare metal does not really offer that much of storage space. So our goal is to really work on persistent storage. We do require persistent storage, as well as we need to be able to transport the data for continuous analyses of the data, because at the end of the day, we feed it to machine learning models and we try to predict whether the data is an attack data or normal data, right? So I did get some solutions already. As I kept talking to everybody here, I would definitely like to try them out. And I think, yeah, that is all I have for the challenges and insights. So now coming to the services, tools, and workflow support. So this work was the integration of 3 different tools. It was the lightweight distributed metric system, as well as the PAPI, which is the performance application programming interface, as well as just TCP dump for capturing the PCAP files. And Metasploit was used for carrying out the attacks. And as well as Chameleon's bare metal was played a very supportive role, in the sense that we could get access to those low-level hardware telemetry. And it is available on GitHub, so it's clearly reproducible. And there are like Docker images that users could just deploy on Chameleon and start using right away. However, the only problem that arises is that those who do not have a lot of knowledge on how networking works in Chameleon, they might find it a little bit challenging to carry out such experimentation in Chameleon, because at the end of the day, we want our system to be persistent and so that it could be used by other people very efficiently. And so recommendations for AI research testbeds. So these testbeds, like I said, must provide persistent access to low-level hardware performance counters, which actually bare metal already does, so thanks to that. And so it could be interesting if it provides container native templates to simplify the security experiments. And also, if there is like an existing way to just to transfer the telemetry directly to the machine learning models, like a pipeline to bridge the raw data that's being collected for analysis, that could be helpful too. And I was actually able to present my work to IEEE CCNC in January of this year. It was in Las Vegas. It was a poster paper, not a full paper. And our work is currently under review at the IEEE ClusterCom. So it's yet to be reviewed. Yeah. And the acknowledgement, it was supported by NSF under this award. Thank you.
So first of all, I'd just like to thank all of you, thank the organizers for giving us a platform to present our work, OpenMCP. I am Anup, and I'm proud to present our work with my good friend and teammate, Augustine. So our work is basically OpenMCP, which is a reproducible benchmarking harness for evaluating computer use agents on Chameleon Cloud. So for a bit of context, computer use agents are basically AI agents that can use a computer like any normal human would. So they can use the cursor, they can type text, they can navigate the computer using CLI or GUI actions. And Modal Context Protocol is basically an open standard protocol for such AI agents to basically interact with applications such as GitHub, Obsidian, Notion, etc. So we are actually like the part of the infamous Spring 2025 semester class that Professor Freda Fund taught. And like the main thing that the class focused on was reproducibility. So with the encouragement of a professor, we actually aimed at first to do a we actually aimed to reproduce a benchmarking paper so that we could create a reproducible paper. But the issues we got was like, there was like severe limitation in like all the existing benchmarks having reproducibility issue. Like the major issue was like all of them were using, most of them were using external APIs to call LLMs, which was costly, and we're graduate students, we don't have that kind of money. And also like most like couple of the papers were using deprecated models that wasn't available anymore, so it essentially made those papers or like benchmarks non-reproducible. So these were like the basic benchmarks that we were aiming to use for reproduction. And using these benchmarks, we were also trying to answer some of our research questions, such as how do agents solve tasks? What kind of tasks do agents find difficult? And how much token are consumed? The existing benchmarks could solve these questions, like, and help us answer these questions, but they couldn't help us answer like more fundamental questions, such as like hardware telemetry questions or like model quantization questions. So keeping in mind that there was like a reproducibility issue in like MCP related benchmarks, and there were also like not that much literature going on in energy or like more hardware level specification, we opted to create OpenMCP. So we actually created it on top of MCP World because that fit our need the most. So I'll just go. So the OpenMCP was actually built on top of a bring your own X philosophy. So if you can look at the architecture, essentially most of the components here are extendable. You can bring your own LLM model. You can host it anywhere. You can host it in the GPU, like in a data center GPU, such as H100, or in an edge instance, and we'll gather the performance there. You can test any applications. For our use case, we used VS Code and Obsidian. You can bring your own task, and you can use your own evaluation script for those tasks. And also, you can get like your own infrastructure telemetry. In our case, we used NVIDIA SMI polling. And like this is just a overall view. For an end-to-end description of how our harness works, I would like to hand it over my mic to Augustine.
Everyone. So we will actually show you a quick demo of OpenMCP. Unfortunately, it won't be a live demo because first of all, it would take forever. And second of all, we all know live demos never go well. So it's gonna be a video. I'll try to do my best describing what's going on. So in this demo, we would run basically a very small experiment in which we're gonna have the agent complete one task in Obsidian. The task is gonna be about grabbing a node and deleting that node, basically. But the interesting thing is that we're gonna start in the demo from the steps 1, which is provisioning resources. So for this, we have our own Trovi artifact that is connected directly to Chameleon. This Trovi artifact will take care of launching the instance and cloning the code into the instance. So in this case, for example, we are using KVM tag. We're finding our lease. And for this demo, we're gonna use a flavor of an 800 VM. This Trovi artifact will automatically deploy the instance. And once the instance is deployed, it will clone the code for OpenMCP. And basically everything will be ready to start actually an experiment. So for this, we put everything, all the configuration together in one single config file. This config file will set different parameters for different aspects of the architecture of OpenMCP. And perhaps more importantly, in this config file, among other things, we would set which models we want to benchmark. Because this script supports multiple models. If we select multiple models, it will automatically benchmark each model. It will flash the model, load the new model. So for this purpose, we will run a benchmark with just one model, a Qwen 32 billion model. So once the configuration file is ready, the OpenMCP has everything it needs to start an experiment. So we will run the entry point script, and the entry point script has basically 3 steps. The first step is setting up the environment in which we will create a Docker image, we will launch containers. The second step is installing the necessary applications where the agent is supposed to take actions. So in this case, we need Obsidian, right? The script will ask the user if they want to install these applications. If the user confirms, they will be installed automatically. And at this point, the benchmark will be ready to actually start executing a task. We want to pause here. And if you notice on the right, at this point, both containers are already running. Both the OpenMCP container, the main container, and the Olama container, which is where we serve our model. And also our services are up and ready. In this case, I'm going to show you the virtual desktop, which is an OVNC. You can see it's an Ubuntu machine, and it's ready for the agent to start taking actions. So once we confirm that we're going to start, we will load the model, if it's not already loaded, and the agent will start attempting the task. So we will see on the right that the agent will open Obsidian, and it will try to delete this node called, I think, archive me. Yeah, this node. So it successfully did so, and the user will get back a message basically notifying them about some stats about the experiment and the final task status for this specific task, which in this case was success. So finally, once all the tasks are run and all the models are run, will come the last step of reviewing the results. And for each task that runs, OpenMCP will create a detailed JSON file that will have, broadly speaking, 4 items. First of all, we have metadata about the experiment. Then we have raw events. We will keep track of everything that the agent did, even the things the agent attempted but it did not succeed at, because this could help researchers track how agents approach tasks. We would also have metrics, different types of metrics, latency, LLM calls, tokens, etc. And perhaps more importantly, something we really care about, we're going to have a specific GPU hardware metrics related to energy consumption, power, VRAM, etc. So after the experiment is done, the user will have a collection of JSON files with rich data. And this data collected by NCP is actually able to answer the research questions that Anoop already described. So, for example, what's the connection between model scale and agent performance? We can build plots like this where we compare different models for different families, different sizes, and we see the success rates. And we can also approach more nuanced discussions, such as what are the trade-offs of quantization? Does it always help? Sometimes does it harm the agent? And more quantization means always less energy or not. And in this case, I don't want to focus in our results, but we find that if we go too far with quantization, actually the usage of energy increases because the agents take much longer in completing the tasks. After we collected the data, we discovered that our data was able to handle actually more research questions that we didn't initially consider. So we collected data from edge devices, so we were able to respond if computer use agents are feasible for resource-constrained devices. And also other questions like connected to confidence, exploring if the models are aware that some tasks are more difficult than others, and if they express basically confidence issues, they are aware that they might mess up, right? So up to this point, we haven't talked about Chameleon, and we're after all in a meeting of users of Chameleon. So I do want to stop here and say that Chameleon was absolutely core to this project. The entirety of this project was developed in Chameleon. I don't think we ever used any other cloud, or we never ran it locally either. In total, we used over 30,000 service units spread over about 6 months of work. All resource provisioning was handled using our Trovi artifact. And I want to highlight how useful were the 800 new VMs that are available in KVM TAC. They were basically our playground. And they became a playground for a number of reasons. First of all, I think they were already discussed. The spawn time is basically 2 minutes or less compared to the over 20 minutes or 30 minutes that it takes to bring up an instance from bare metal. But on top of that, setting everything up, you're looking at easily 1 hour of work. And when we were working in this project, we would work about 3 hours a day, let's say, on this project. So we would be giving 30% of that time to setting up the resources, and this project would have taken certainly much, much longer. Since they're also in KVM tag, we can create the instances from volume storage. So we have a persistent development environment where we can pick up where we left off. And this volume storage also enables us to play around with very large models, which is incompatible with the small storage in bare metal. And on top of everything, the 800s are top-notch GPUs that are very popular, so they were really the perfect choice for us. Some minor issues that we faced was already discussed, the inability of using Python Chi for launching instances from volume storage. I understand that it's already been taken care of, so I think that was our main issue. A part of that, our experience with Chameleon was awesome. And so just to summarize, OpenNCP is a reproducible benchmarking harness for NCP-enabled computer use agents that gives full control to users and also collects rich data for metadata, metrics, and GPU telemetry. We have an upcoming paper for the AeroMLSys workshop of the AeroSys conference coming up by the end of April. I'm making available through this QR code our Trovi artifact. In case you want to try this tool, give us some feedback. We would love to hear from you. And I would like to end up thanking the Chameleon team for such a great platform. It really made this project possible. I would also like to thank Professor Farah Fant because she gave us amazing guidance throughout this project. And thank all of you for your time today. Thank you.
Hi, everyone. I'm Sujay. Happy to be here. I'm a postdoc at UT Austin. So a little bit about myself. I got my PhD from Wisconsin-Madison. I started working on computer architecture, um, and then I started working on Intel Optane. I don't know how many of you have heard of it. And 2 years into my research, Intel announces that they're going to kill the product, and I'm like, okay, I need to pivot. I need to adapt. And that's when I said, okay, if I'm adapting, let me work towards adaptive systems. And that's what brought me to LDOS. So LDOS is a NSF expedition where we're trying to see how ML and AI can help operating systems. This has researchers from UT Austin, Wisconsin, UIUC, and UPenn. So I'm sort of giving you an overview of work that's being done across all these institutions. So I want to start us off by talking about operating systems. Most of us know what it is. It is the core resource management in most systems today, be it mobile phones, be it the cloud, be it edge devices, right? And their main task is to manage resources such as your CPU, memory, storage, network, and so on. Now the problem is that modern day applications are becoming extremely diverse. They have various requirements, and these requirements are different. You have user-facing applications that have strict latency requirements. You want a response within a few milliseconds, and then there's like throughput-oriented workloads where you want good performance for a long time. And the thing is that all these applications are working in diverse environments and different conditions. You have robots that are helping out humans within, say, a building. You have things running on the cloud. And the problem is that the operating system foundation that we have has a very has a very rigid structure to it. And this causes problems, as I'll show you. So there has been plenty of research that has showed that because our operating systems are rigid and not really adaptive, we often waste resources. We fail to meet certain requirements. At UT, we were doing an experiment with some robots. And so here's a simple example where the robot does extremely well when it just has to run the navigation task, right? So it's doing a great job. It's avoiding all our obstacles. And then we did a simple thing. We introduced a user application. This is just like a third-party workload that a robot might have to run. And as soon as we did that, we saw that the robot struggled to navigate. And we said, okay, this looks weird. A robot should be able to do this. Like, this is bare minimum. And when we sort of, did some debugging, what we realized was that the scheduler, so if you guys are familiar with Linux, the default scheduler until last year was something called the CFS, is not really meant to, meet the requirements of this robot, which has real-time deadline constraints. So these are the kind of problems that we face with existing OS structure where it's rigid and you cannot really meet the requirements of modern applications. So just going down deeper, we believe there's two main reasons why this happens, why this structuring of the OS is problematic. The first is that the OS comprises of different policies, each of which manages a certain resource. For example, you have a scheduler, you have a page allocator, you have, say, IO scheduler, and so on. And conventionally, the way we build it is by expertise. There's a Linux expert, Linus, or whoever. They have some insights on how the scheduler has to be built, and they kind of focus on that. They use some metrics or heuristics that they want to rely on, and then they build this design. Right? And the second philosophy is that these components or these policies are built in isolation. A developer who's looking at the scheduler doesn't really care what the allocator is doing or what the IO subsystem is doing. And this myopic view often leads to destructive interference. A system one is trying to optimize for a different goal, policy two is trying to optimize for another. And therefore, when it comes together, you don't really get the best of performance. And this is sort of prevalent in not just the robot scenario. We've kind of seen this in different use cases, be it the cloud, be it the edge cases. All right, so what are we doing about all of this? So our goal, our vision rather, is to have a self-customizing adaptive operating system. And to achieve that, we said, hey, let's use ML. All right, because ML has shown promise in other fields. So we said, maybe it can help the operating system. So the idea is simple. You have an operating system that uses learning and can, be more adaptive and adjust to different environments. So in our case, we want to have this, single central OS that kind of adapts to different scenarios. And usually this is when I see a lot of raised eyebrows and people kind of not agreeing with using ML in the OS because there's a lot of problems. And I'm going to get to that. But before that, just a quick overview of how our approach works. The idea is simple. We collect some training data, we build some models, we launch them into the operating system. The operating system has certain monitors that it uses to make sure that we're getting the performance that we need. And if we are not, we might switch models. So we're basically saying, hey, maybe the model that we trained is not really good for the scenario that we are running currently. So maybe let's just change the model or retrain and so on. So just a couple of challenges with this approach. The first is that if you want to have ML-based policies, you want to have easily pluggable policies. But today's operating systems are kind of optimized, hyper-optimized, and so policy and mechanism are kind of entangled. And as a result, it's really difficult to just replace a policy, like pull out a policy and swap it with a learned policy. So we need to do some hand-holding, massaging there. A related problem is that sometimes when you're using learning, you want to gather data from different sources. But with current OSs, it's sort of difficult because some of the data is buried in certain abstractions, and so it's not really easy to use data from other subsystems to make decisions. A second problem is that we all know if we have a learned model, it's data hungry. It's as good as the data that it's trained on. So we need to gather a lot of samples or data for training. And this is not really easy in the operating system world because this might involve running applications for a lot of time in different environments. And so collecting data can be quite challenging. The third is the obvious, which I'm sure a lot of you might have thought about when I said ML inside the OS. ML has overheads. Running a neural net might be expensive, and operating system decisions have to not take more than a couple of microseconds. Even that might be a lot. So how do we realize this goal of ML if we want low overheads? That's a challenge. And then the last is that ML decisions might not be robust. They are black boxes at the end of the day. We don't really understand what they're doing. So it's difficult to trust them and rely on them for good performance. So at EndLaws, we're trying to tackle each of these problems. I'm going to kind of quickly skim over how we're doing this. To tackle the problem of poor OS structure, we're building a new operating system, a clean slate operating system that has this policy and mechanism separated. To handle the training data requirements, we're looking at how we can build synthetic traces. To handle complexity, we're looking at different types. One is using accelerators within the kernel, which might seem crazy. And the other is sort of the LLM evolution framework, where we are trying to convert a model into a heuristic. So we're saying, hey, if a model is making certain decisions, can I convert that to a code or a heuristic? And we're trying to see if LLMs can help us do that. And last, to tackle the robustness, we are looking at guardrails and formal reasoning. I'm gonna go over each of this really quickly and then talk about the infrastructure and software challenges that we face. But before that, yeah, so I told you that we're working on a clean slate OS. We're calling it Mariposa. It has two goals, policy mechanism separation, and the second is being able to observe data from different systems. So to achieve this, in this new operating system that we're building, we're decomposing every single policy and mechanism into servers which are replaceable. So anybody who's developing a policy for our system can just pull out a server and plug in something that they have built, which makes it easy to replace policies. And with regard to the observability, we have this structure called OQs. These are like queue-like structures that the servers use to communicate. And these structures are global, so anybody in the system can observe what's in the queue and use that to make decisions. This figure sort of shows that example. If I have a file system and a prefetch policy, I have each of them implemented in different servers, then there are queues between them, and anybody can observe them. The second is about the trace generation. So we recently had some work done, accepted, where we looked at how LLMs can be used to generate synthetic traces. And in this particular project, we looked at how we could generate microservice graphs. And the goal that we had was to prompt an LLM saying, hey, generate me a microservice graph that's realistic so that I can build a policy that's optimal for it. And so to do that, and the goal was to generate such synthetic traces. So to do that, we did some pre-training on some small set of traces that we could gather. And then, we have this fine-tuned LLM that could generate this traces. The next thing is about overcoming overheads. And I said what we're trying to do is generate heuristics. This is very similar to the keynote idea of using LLMs to optimize code. So what we're trying to do here is ask an LLM to generate heuristics that are specific for a scenario or convert learned models into heuristics. And the idea is, we have such heuristics per instance, and then an instance can be a particular hardware, it can be a particular application or a combination of both. And then when you move to a different instance, you're running it on a different machine, you might have to generate a new heuristic. And this is something we are currently working, and we'll soon have some results about this as well. The last thing is about guardrails. So I said, we can't trust ML, so we need a way to do something about it. So what we're building is a monitoring framework that looks at looks at multiple things. It looks at the input, it looks at the ML output, and basically says, hey, is the system behaving like I want it to be? For example, is the input within the distribution that I have trained on? Is the output within the range that I would like? Am I satisfying the properties that I want? And if these guardrails trigger, that is, they say, hey, we are not actually meeting the goals that we were set out to meet, then the user can specify actions to fix that. You can either change the model or fall back to a default, and then avoid such poor performance. So there's a lot of work that we're doing in this field. Here are some other projects. I'm not gonna go into the detail, but if you're interested, please do look at our website. There's some really interesting stuff there. All right, so now coming to the part where I think some of you might be interested in, which is what are the challenges we faced when when researching on ML or AI for operating systems. The first thing is reproducibility, and I'm sure this is a recurring topic, everybody brings this up. But in our case, it's slightly different. Since we're working on the operating system, we want reproducibility in the at the kernel level. So for example, there's a lot of kernel parameters like sysfs parameters, which are not usually captured in images, which are not captured using snapshotting. Currently, the way we handle it is by having scripts that we run, but this is very ad hoc, there is no standardized way. The second problem is that we want to reproduce certain state. For example, we want to reproduce memory fragmentation. And there's no real way to reproduce that. So we have some fragmentation tools that we run, but there's no real way to reproduce. The second problem is that of portability. So since we're building this adaptive operating system, we want to try out on different machines. And so we want to port our design, our system to, our policy, our system to different hardware. But then many a times there are certain settings that we need to change. For example, there was a project where we were doing something with NUMA, and we had trained on a two NUMA node machine, and when we had to go to a 4 NUMA node machine, we had to change all our scripts because it was sort of hard-coded for this 2 node machine. Another problem, I think this was brought up earlier in the morning, is that we have seen variation in performance across nodes of the same type. And we really don't know why this is, but our hypothesis is this could be things. So for example, we see variation in storage performance, and we believe this is based on the age of the device. Maybe one SSD is older than the other, so it's more fragmented. So there's block level remapping happening more frequently on one than the other. So we get different performance on the same hardware. So that kind of makes our research even more challenging. The third is with crashes. Since we're working at the operating system level, when we make a mistake, there's a bug in the code, and there's a crash, we need to be able to reboot quickly. This is sort of difficult. I think during lunch we spoke about how reboots can take a really long time. So we need a way to be able to reboot quickly, and there is no easy way out for this today. There are some software challenges. I'm gonna not go into detail, but these are more about how to collect and manage data. There's no framework, and then how to deploy policies that are written in Python. And if you want to, kernels are usually written in C or C++. And so how do we go from Python to C? Yeah, that was what I wanted to talk about. If you're interested, please use the QR code to go to the LDOS site, where you can find some information on the work that we're doing. Thank you.
I had a question for Aaron, I guess. So some of the kind of challenges you encountered, things like managing data across experiments and managing like versions of data and models and experiment tracking. Some of these are to an extent addressed by the field of MLOps. I was wondering, do you think that perhaps like a Chameleon tutorial sequence on MLOps for researchers would have been something that's helpful for you?
I think so. Yes, I could look into it. I could definitely look into it. So the main issue that I was facing was that the attacks that we run, so we run like several hundreds of 40 gigabyte attacks. So let's say there's one session which is like taking 40 gigabytes of space. We run like hundreds of those. So I was good with archiving the data, but like also running, fitting the data to the models, and as well as analyzing the data is what I was struggling with.
Like
Because I had to like store it somewhere, pull it, and then use it on a different device.
So this is very similar to the problem that we face. I mean, I kind of skimmed over it, but this is something even we sort
Data
of...
engineers know about this stuff, but somehow they keep it a secret and no one else knows how to do it.
So a tutorial would be a good idea. Yeah.
But thank you so much for mentioning it.
Irene, I also have
Yes, go ahead, please.
Virgin,
No, no. No, Mark sent me a bunch of questions to bash Chameleon, so please.
You mentioned the need for persistent storage to feed the pipeline. Were you not able to use the object store for that purpose, and why?
So, to my knowledge, the object store was just for archiving the data, but I could be wrong.
Not
Because I'm up, so just to give you a little background, I'm more like a networking person. I'm not a very systems person, so I'm still learning. I've been working with like HPCs for just the past
Any
few
reason
months.
why object store couldn't be used?
No reason at all. I think it's just
This is a data
your
engineer
expectation
problem.
from what was available. And the system can do more than you thought, right? Is that what I'm hearing? Yeah, I think there's a big opportunity to use the object store both to stream data into from your experiment and then pull it back out for analysis.
But can you like carry out the analysis in the object store?
What you would want to do is like, you'd have
So-
like your initial loading raw data into object store. And then you'd have a separate job that like processes it, so pulls it from the object store, does some processing, and then puts back the process data for training. And then you'd have another setup where, let's say, when training a model, you'd be streaming that process data and training on it directly from the
So,
object store.
so I think your question is whether you cannot operate on the object store in situ. No,
That's
you have
just a
to-
storage space.
You have to copy it back out to work on it. So, this might be a good case for something more like the NFS, Ganesha, that is.
You wouldn't even need that, like, the standard, like, data engineering way to do this is like, you have an ETL or an ELT pipeline, and you load it, and you process it, and you load it back into the object store, and then you could stream it for training.
Yeah, so I think maybe like a tips and tricks blog on that topic would be good.
I'll take notes.
So that-
Thank you so much.
But so that others don't have the same problem, right? So it's an experiment pattern that might be useful for many.
I'd also be really interested to find out about any limitations you run into. For example, not having enough local storage for something came up, I believe. And so, there may be some ways that there are some easy wins.
Yeah, just piggybacking on those questions, if you, while you're using the testbed, if you felt that some functionality was lacking and you really need it, question number one, and number two, when you were running workloads, in particular workloads, did you feel some of the workloads were more challenging or more difficult or even impossible to run on Chameleon?
Well, not really. I mean, I was happy with the way it performed. So I would say no.
So is that a question just for?
No, for everybody.
Oh, okay.
No,
So
sorry.
everybody should say, yeah.
Yeah.
Sorry, could you say that again? The question?
If when you're using Chameleon, if there was some feature or some feature that you would like to have had in your workflow, but you didn't, or well, Chameleon didn't have it, and when you're running workloads, did some of those workloads give you more headaches than others, or more challenging, or impossible to run on Chameleon?
Yes. So we did have one issue, and I just want to say that I really like and support what Paul mentioned about the discovery of resources. Yeah. Because at some point in the project, we had run some experiments in bare metal and 800 VMs, and then we were done with them and we wanted to run experiments on Edge. And we're not Edge experts. We don't know, like, if you tell me Jetson, I don't know how much RAM they have. I don't know how much storage they have. And we had these models, right? So we needed to know if the models fit in the devices, and it was a bit difficult to explore that. At the end, you had to kind of like deploy an instance in the device, and then you find out exactly how much RAM they have and how much availability they have. So if we could add on top of all what you mentioned, where we see all the resources, their availability, and also confirmed data about how much RAM they have, how much storage they have, so that it makes it a bit easier especially for people that are not experts in Edge to run experiments on those devices. So, yeah.
Yeah, and like on Edge as well, like it would be useful if we could easily go inside the container, like they use a Docker container to run it, right? So to monitor, because what we found out was like when we were running models in the container in Edge, we weren't sure if they were working or not because we tried directly from using Python key to execute a command, and it used to just stop in the middle, and we didn't know if the device was it was facing any issues or not. And when we tried to go inside, try to get more data, information out, we couldn't use it. We couldn't directly do it from Groovy artifacts. So we had to go into the instance, go into the actual UI, the log UI from the web browser itself, and try to figure it out. So yeah, it would be easy if it was easy. There was an easy way to go inside the instance or the edge, same as we can do in bare metal or the KV, the virtual machines.
So I had a question today that how do you pick your nodes? And I'm I pick them randomly. I don't know how I pick them. So I didn't know about the documentation until today. And
The documentation
as
exists.
in what's it called again?
Research discovery.
Yes, I didn't know about it until today. So I think that should be helpful.
Okay. How did you find out about Chameleon? Did you do Chameleon quick start?
Well, I found out about Chameleon because of Dr. Moore.
I see.
That's how I found out about it.
Okay, so you never did Chameleon quick start or any kind of read documentation before you?
Yes, as I started working on it, I did read through the documentation. However, I didn't know about this particular
The browser.
the browser,
The browser.
because it tells you about the availabilities, right?
But that
It
means
does,
that
not
we
today.
need to-
But
It links to it.
We need to improve onboarding for people like you, clearly, because it's an important feature.
absolutely.
Similarly, for Cheat Edge,
It does have logs, right?
yeah,
Python Cheat does have logs, right?
Python G has logs. Some of the information you're looking for is in the docs, but it's harder to find than it should be. And some of the ways to get into the containers we do have, but it's harder to find those examples than it should be. For anyone who's interested, we'll be doing a tutorial on using Cheat Edge for this kind of thing tomorrow. And so I'll be showing some of those methods, and I think should be a great time for Q&A and kind of digging into it.
But it's definitely true that Edge has a lot less visibility into what's going on than all of the other things.
Yes. So a lot of this stuff is kind of known gaps, but it's helpful to have them kind of highlighted about, this one's a particular blocker, this one's important, because it helps prioritize.
So going back to the question, regarding workloads, I don't think we have had a problem running any sort of workloads. We have been able to run whatever we have liked to. I think our problem has been more with hardware availability itself or operating system related stuff. For example, we have projects related to CXL, but CXL is something that's not available, not just on Chameleon, but a lot of test beds. So getting access to certain types of resources has been a challenge. And then regarding features that we would have liked to have is, I think going back to my slide, snapshotting memory would have been nice if we could on a bare metal or maybe even with KVM instances, if we could snapshot the entire memory, that would help us. If we could snapshot the kernel state, the variables and all of that, that would be useful. Right now, we try to reproduce that by running a specific set of instructions, which could take 15 to 30 minutes, or sometimes even more in case of fragmentation and stuff. So if we could fast track that, and that would be helpful.
You can't just crash the node and get a cord up? I mean, I'm serious, I'm not joking.
So we need things like, let's say, the queue depth, for example. I want to know what is the load on each CPU queue, or I want to know how many requests are pending in an IO queue.
I'm just talking about memory. You want to snapshot memory?
Yeah.
You can just crash a node and it'll write the memory to a disk for you. You have to set up a crash kernel. I'm talking system stuff here, and this may be one of the things too, right? The kind of systems knowledge that we have to do these kinds of things. Maybe y'all don't have. So I would know how to do that, but you might not.
Does the crash record the entire memory state?
Yeah, what you do is you start up, you take a little piece of the memory and you save that for running a crash kernel. So it can run a kernel, and then when you crash it, you literally you pass
Interrupt.
you write something into proc, there's a systems request, you write a C into that, which crashes the machine. And then the crash kernel will take over, and then it'll just take everything that's in memory and dump it right to disk.
I see. Yeah.
Now, you have to have local disk, or you have to have NFS mounted disk, or you have to have storage space for the amount of memory you need, but there are easy ways of doing this with a system. But again, maybe that's the things, maybe there's some systems things that we can do, right? Systems you can share with your researchers, right?
Yeah, I think that would be helpful for sure.
And I guess the flexibility of adding, I'm not sure how easy it is to add your own monitoring on top of the nodes. Like you mentioned, the CPU queue load, right? I'm not sure if that's a feature that the Linux kernel would provide. I'm not that familiar with low level.
So it provides some of these on the sysfs and the procfs interface, but we need a way to save that and kind of restore it to that.
Yeah, crash the machine.
And it sounds weird to say, I'm gonna just crash, but that's how you copy memory, that's what you do, right?
Or, you have a layer of monitoring that you install yourself.
So that's what we're doing currently.
And this is just for bare metal, right?
Yeah.
Because for VMs, you have all that.
Yeah.
One thing I will mention, just in case it isn't part of your workflow, you can take one of our images, install all these various tools, and then snapshot that image, and then use that as your base for future work.
So the tools are installed, but you still need to run the tools. So that takes up time. So that's all.
Gotcha.
We'll probably take one more question before we go into the break. Yeah. Or
I'm gonna ask.
Go. Okay, I'm sorry. Go. No.
I'll ask Irene.
2 questions. Please go ahead.
I have a question for Sujal. I was wondering, you mentioned that you train a model as a replacement for the original heuristics that sits on the OS. Have you also measured the cost of running the inference on the ML model for determining the optimal resources? I mean, did you look at the overhead in addition to the accuracy that you get?
Yep. So that's also, I think one of the challenges I mentioned is the overhead. So the models that we try to run are really small. It's either like a single layer neural net or a decision tree or a simple regression model. So usually we try to keep the latency, the inference latencies in the order of a few microseconds. We try to optimize it, we try to batch and as much as we can. So there are certain subsystems where we cannot achieve the required overhead or the low overhead, and at that point we have to try to replace the model with a heuristic that resembles the model. So for example, a scheduler, for instance, you want really quick decisions and you can't afford to have learning there. So there are certain cases where, for example, if you take a RAID device and you want to do some admission control, because storage latencies are in the order of, say, high microseconds or sometimes even low milliseconds, you can afford to run an inference. So there are certain places where we're able to use it, certain places we are doing some optimizations to replace learned policies.
Optimus, you have maybe one more question.
Sure. I can ask one question. Is it okay if it's not strictly related to Chameleon?
Yeah.
All of you are training agents or are using AI to try to solve a systems problem. And you all mentioned more or less that one of the biggest issues is AI is trying to take shortcuts, trick you, hallucinate. How do you deal with that? And how often do you have to deal with that? Yeah, that's a question for everybody.
Okay, I can. If you want. All right. So I'll just give you an example of something that I saw maybe 2 days ago. So we're using LLMs to synthesize heuristics. We saw for a particular memory subsystem, we saw performance improvement of like 30%, and we said, okay, this is insane. Like, 30% in the operating system world is like a game changer. And then we were like, okay, let's see what the LLM wrote. And then we looked at the code. It's just a bunch of values. That's like 1.5, 0.25 into something, 0.65. So it's like so hyper optimized and like it's a parameter tuning sort of problem that it's like it does so well only for this particular workload on this particular hardware. So the problem again, as you said, is it's doing something that we might not like. It's doing well, but it's not something that we want. So now we realize that the way we would have to prompt it is to make it build generalizable policies. Basically say things like, hey, don't over parameterize or don't overfit. Try to make it work for more than this scenario. So this is just one of the examples on how we are trying to avoid the problem or overcome the problems of AI.
In our case, which was more like agents trying to complete a task, like do this, do that, we did encounter some issues for which we implemented some metrics dedicated to that. For example, you know how in MCP you expose some tools to the agents that they're allowed to use at some point. For other tasks, you might not give them the same set of tools, so that depends on the task. And one thing we noticed is sometimes they would call phantom tools that did not exist. So we kind of like implemented a very simple like script that would detect when would that happen, and so we keep track of that and we count it and we measure how often that happened. For our results, it didn't happen that often because I think our tasks were fairly simple, but I think it would happen more frequently for more longer, more complex tasks. We also implemented a way to detect when this happens more frequently. The agents get obsessed with one way to approach into something, and they struggle with change direction. And so when they would call insistently a tool 3 times and get failed, we would like just call it there, and end the execution because it could go forever. And basically, for task completion, we noticed that if they don't get it right during the first seconds, if they don't get into the right path in the first seconds, they're gonna start to do weird stuff. We have issues of an agent trying to break the sandbox because we direct them to a specific directory where they can play around, and they're not. We put protections, but they would try to break from there, and that would usually happen when it's too much time trying the task. So it's generally a good idea to put a limit. You don't allow them to attempt a task for 30 minutes. Depending on the complexity of the task, but in our case we use like 5 minutes, I believe.
Yeah.
And if it's not about 5 minutes, it's considered failed.
Like some of the weirdest case we saw was the agent tried to install a random package, like some deprecated package from like way back, I think 10 years back, for like just a simple task of moving a file from one place to another. And that was like an extreme case we found out. And also like in our harness, like what we set out was the evaluation would be deterministic. So we will always have like a strict binary, like did the agent pass or fail as well. So that way we can also evaluate them.
So in my case, it was more about understanding how good is really good. So when I say that, as we were working on integrating system level matrix and network level matrix, there weren't many papers that I could compare my results with. So there weren't many network intrusion detection data sets that I could compare my data with. And also, I asked Mr. Richardson to change my slides. So as we were working further, we actually got better results than we did in our previous experiment. So I actually sent you the wrong slides, and so I had to update the results section. So we saw that as we traced back to what was really creating the problem, because with learning models, it's really important what you're feeding to the model should be of good quality for it to respond accurately, right? So whenever I get results which seem a bit off, I always trace back, because with attack data, you can always miss one thing or the other. So, and apart from that, like I mentioned, it was really, right now the main challenge is really understanding how good is really good. So we have very few state-of-the-art that we can compare the current work that I'm doing. So it's kind of like, you can say that was like the challenge, like to establish a benchmark, or at least to figure out what benchmark to compare it with.
I just remember this famous saying, I forget who said this, they said all models are wrong, but some are useful. So,
I think it's George Box.
yeah.
All right, well, I don't want to cut into the break too much longer, so.
Can we get a round of applause?